Thanks, Bruce. Good afternoon, everyone. My name is David, and today I'm going to walk through some of the improvements we made for modeling salts and hydrate equilibria. And so this electrolyte model extension builds upon our previous work for the cage-based hydrate model we developed at Equilibria. And so what's unique about this electrolyte model is that it requires only 3 parameters per electrolyte, with no additional parameters for mixed electrolyte solutions. And in terms of how we obtain these parameters, they're purely predicted for hydrate equilibrium data. And so I'm going to walk through some results where we've assessed the hydrate model with the extension against Multi-Flash 7 for a range of simple and complex aqueous systems, which includes from single salts to 2-salt mixtures to a formation water that contains as many as 6 salts. And for a particular black oil, we see that the average error is on par with Multi-Flash. So I'll eventually get to that. But before that, what is the motivation behind all this work? And so it comes to the design point where we're looking at the expected pipeline pressure temperature profile of a flow line from your wellhead to the shore. And ideally, we want to identify the regions of the pipeline that are going to be at risk of forming hydrate and the lowest temperatures that the pipeline will reach. And so we use models to predict the expected hydrate formation curve of the fluid, and we overlay that on the pipeline to get that answer. So the problem is that these models have associated quantities of error, which we can call the average absolute deviation or the overall uncertainty of the model, and something that's called the bias. And the bias highlights the conservativeness of the hydrate model prediction, or in other words, whether it's going to overpredict or underpredict the hydrate equilibrium temperature compared to the actual hydrate equilibrium temperature. And so what's interesting about the models is that these error quantities aren't static, they're going to change your fluid composition. And so what you often do is to inject a thermodynamic hydrate inhibitor such as MEG to shift the hydrate formation curve such that the pipeline pressure temperature profile is no longer in the hydrate forming region. But when you do this, your uncertainty, the associated uncertainty with the new system containing MEG is going to be different. And so it becomes quite important to understand these associated metrics with your hydrate models, as well as build a hydrate model that can minimize your associated uncertainty and be confident in the accuracy of the model. And so what this means overall is that when you're developing a strategy around preventing hydrate formation in your pipeline, that you can try and reduce the amount of MEG you have. And by reducing the MEG doses, you can have savings in your capital expenditure from having a smaller MEG facility, if you know that you're going to design around the lower MEG dosage. Less operating costs as well as a lower carbon footprint. And for existing assets, the ability to extend your operating envelope beyond its original design by using an improved strategy. So that's the motivation behind this work. And so next couple of slides, I'm going to talk about the basis of modeling of hydrate in terms of the thermodynamics. How do we actually determine the equilibrium temperature? And so it comes back to determining the chemical potential of water in the hydrate phase. And the starting conditions that we consider for this is, what do we actually need to form hydrates? Well, we need water molecules and gas molecules at high pressures and low temperatures. And in terms of describing this chemical potential, there's essentially 2 key terms. So first, you have the energy change that's associated with forming the empty hydrate lattice itself. And secondly, you have the energy change associated with the cages of the hydrate lattice being occupied with gas molecules. And so in UWA, we've developed a new cage-based hydrate model that improves on the second part of the description. And so we're concerned with something called the fractional occupancy in this regard. So that describes what proportion of your hydrate cages in the lattice are going to be occupied by a given gas molecule. And this is described by something called Kihara potential parameters. So the Kihara potential is what we use to describe the interaction of the gas molecule with a given water molecule that makes up the hydrate cage. And so this is a graph that shows the intermolecular potential as a function of the distance between the molecules. And if we look at this, we can assign these parameters some physicality. So your first parameter A is basically the minimum distance that your pair molecules can approach each other. If you increase this distance slightly, you reach the point sigma, which is where you have no net attraction or repulsion between your two molecules. And then finally, you reach a point epsilon a bit further along. That's your maximum attractive potential between the molecules. And so as you go beyond this point, the intermolecular potential begins to dissipate. So the traditional approach in hydrate modeling is that you have one set of key potential parameters that describes all of the interactions of the guest with the water molecules that make up a hydrate cage in all of the different cage or cavity types. And because if you consider that the cage itself can consist of 20, 30 water molecules all interacting with this one guest, and that interaction changes depending on the exact position of the guest within the cage, it becomes mathematically difficult to try and sum all of these interactions. And so to simplify this, what's often done is you consider a spherically symmetric potential. So using one dimension, which is considering the position of the guest molecule in a given radius, then we can use this relatively simple integration to sum all those potential interactions of the guest with each of the water molecules making up the cage. So we've done a new model that looks at tuning these potential parameters, which are previously universal across all the different cage types, to be specific to each of the cage types. So we consider this cage structure of structure 1 and structure 2. You'll notice that they each have a small and a large cage. The small cage type is actually common to both structure 1 and structure 2, while the large cage types are different. So we use this advantage to give the large cage potential parameters the physical description that separates structure 1 from structure 2, as well as the number of cages themselves per unit cell. And so by assigning the guest water interaction to be unique to the cage type, we improve the physical description of the hydrate itself. So in practice, what this means is you have a set of potential parameters for your small cage that's common to both structures, so for something like methane. If you want to model methane simple hydrate as a structure 1 hydrate, you have another set that describes its large cage. And if you want to model methane as part of a larger multi-component mixture, that's typically structure 2 hydrate, then you use another set of potential parameters specific to this large structure 2 cage. And so by being able to focus on this improved description of the guest water interaction within the cage types, we've been able to strip down on the other parameters of the hydrate model relating to shells and the empty lattice. And we basically, compared to previous models in the literature, notably the Ballard and Sloan, we reduced the number of just parameters by about 40%. So this is the work that I presented at last symposium. So now we're going to look at how do we then begin to consider the effects of electrolyte when using this hydrate model. So what steps are needed? So it comes down to considering how do electrolytes actually interact when we're determining hydrate phase equilibrium. And so the key condition for hydrate phase equilibrium is you're looking at the equality of the viscosity in the water or the fluid phase compared to the viscosity of water in the hydrate phase. And the hydrate phase itself is actually stable when this quantity is lower than this quantity and in your initial pass of the algorithm. And so the hydrate phase water viscosity is described by the CAS model, as I just walked through. And alongside the CAS model, we use the cubic plus association equation state to model the fluid components. And so we use this because that is the best model to account for molecules that hydrogen bond in mixtures. And so the cubic plus associated equation state, it can also account for the effect of thermodynamic hydrate inhibitors such as ethylene glycol, known as MEG or methanol, but there's currently no way for it to capture the effects of electrolytes. And so how do electrolytes themselves interact with the water viscosity in the fluid phase? Well, it turns out that electrolytes will tend to, they're basically a correction factor. So we use something called the water activity, which can be experimentally measured as the vapor pressure of the electrolyte solution compared to the solution that only has pure water. And that acts as a correction factor that will always lower the water viscosity. So it's always going to be a quantity that's 1 or lower. So you have your fluid phase equation state, and you have your contribution of water activity from any electrolytes that you have present. So if you didn't have any electrolytes, this value would be 1. But as soon as you have some salt present, like sodium chloride, you're going to have a correction factor that lowers the water viscosity. And so mathematically, if you lower this left-hand side of the equation, that means in order for the hydrate phase to meet that left-hand side of the equation being lowered, you're going to have a lower hydrate equilibrium temperature as a result. And so the water activity is something that decreases with your increase in salt concentration. And it's something that can actually be calculated from something called the osmotic coefficient. So there's a direct relationship between these two. So by accounting for the effects of electrolytes in this way, we've established a new cash-E electrolyte model that's completely predictive for hydrate equilibrium. So the next couple of slides are going to walk through how we actually did some of the steps to achieve this. And so let's take a step back and consider, what we actually care about electrolytes and how can we measure the properties of their solutions. So basically it all boils back down to activity coefficients. So all the ways that you measure electrolyte properties physically are all related to activity coefficients, and that relates to how you can use various models in literature to calculate their properties. And so the first way is on top right, you can have ion-stacked electrodes immersed in the solution. So you measure the pH, essentially the concentration of your ions. Secondly, as I discussed, there's ways to measure the vapor pressure of the solution to determine the effect of the salts. So you have one solution that has your salt mixture of interest, you measure the vapor pressure of that solution, and you compare that to the vapor pressure of a solution of pure water at that same temperature. The third method is something we call osmotic pressure. And so this is an example schematic. So you can consider that you have a membrane. On one side of the membrane, you have your pure solvent only. And then on the other side of the membrane, you have your solution, so your mixture of your salt and the solvent, which is typically water. And then you measure the pressure on both sides of the membrane and you obtain the difference. And so that difference in the osmotic pressure gives you something called the osmotic coefficient. And so what we've developed in this work, without showing all the maths involved, we have a new osmotic coefficient model for single electrolytes. So it's primarily a function of your electrolyte concentration. And if you're familiar with electrolyte theory, it's an extended de Baeyer-Huckel model. And we have 3 adjustable parameters per electrolyte. So very briefly, going into the verification of this model against experimental data. So here is a number of bivalent salts, and for pretty much all of these salts here, we can see that our new electrolyte model fits the osmotic coefficient experimental data quite well. The only slight exception here is for zinc bromide, and that's because this model is primarily designed for strong electrolyte solutions, and zinc bromide is not a particularly strong electrolyte and it experiences some speciation. But given that the salts that you typically encounter in your formation water are going to be sodium chloride, calcium chloride, magnesium chloride, all of those which are strong salts, you can see that this model is quite reasonable. So we now have a model for single salts. How do we then account for the effects of mixed electrolytes? So in order to achieve this, we use something called Zamenhofsky's rule, which you can boil down to an ideal mixing of water activity. So basically what you're doing is taking the advantage of the fact that for a given mixture of 2 electrolytes or more, but in this case, it's easier to explain in 2, you have lines of constant activity based on the electrolyte concentration. So you have different combinations of electrolyte concentration that give you the same water activity, where you have endpoints where you can describe the same water activity using only one respective electrolyte of that solution. So without making it too complicated, it boils down to a guess and check method essentially. So you're trying to align this ratio on the top here, such that it intersects with all the water activity for a given path. And basically, if you overshoot that path at first, then you can try and reduce the water activity by increasing the corresponding electrolyte concentrations and vice versa if the initial activity is too low. So by doing an iterative algorithm, which is ultimately the Newton-Raphson algorithm we apply, then we can achieve water activity of the electrolyte mixture without any additional parameters needed. So this is how we've developed our electrolyte model. The Now I'm going to walk through some of the results we've been able to achieve with the combined case-specific electrolyte model, which I'll call the CASH model from now on. So this is a box and whisker plot looking at the range of experimental data available for systems containing at least 75% methane inhibited with sodium chloride only. So we're looking at range concentrations from as low as 3% up to 27%, and we're comparing against the CPA Hydrate model from Morning Flash 7.0, as well as the Ballard and Slade model from CS and GEM. And so the box plot also gives you information about the mean and the median, as well as the expected range of deviations that you can expect based on experimental data within each concentration band. So what we can see here is that compared to the other two models, the CASH model performs quite well, particularly below 28%, and above 28% actually tends to perform best. So we see quite a small spread that's close to zero here, and here the spread in terms of width is similar to the other models, but it's much more centered around zero. And so this is quite a promising result, given that sodium chloride is going to be your most common salt in formation water typically. In reality, however, your formation water is going to contain mixtures of salts, including other salts such as calcium chloride, which we look at on this slide. And for this salt, we see similar performance as well, where the CASH model performs quite well across the board. So it performs better at these high concentrations, and you see it performs particularly well in this 15 to 28% range. One thing to note as well is that even though that there's not a lot of data for this 3 to 5% range for calcium chloride in particular, all the models predict this system quite accurately. This might infer that predicting the effect of electrolytes at low concentrations is not as difficult as predicting the effect at the high concentrations here, which is why you get these good predictions even though there's not a lot of associated experimental data. Now that I've covered these sort of general cases, let's look at something more specific. So we're going to look at a natural gas example that has formation water. And so this is the composition on the left-hand side. And basically we have two salts that contain 5 salts here and 6 salts here, primarily sodium chloride in each of these mixtures. And we can see that the CASH model, which is implemented in our software, Thermofast 2, and CPA Hydrate from Multiflash perform quite similarly for the experimental data shown here, where on average, the average deviation is slightly above CPA Hydrate for the CASH model, but it is within your typical experimental uncertainty of about 0.1 to 0.2 Kelvin for these more complicated systems. So we can see that the CASH model holds up quite well for a natural gas that has a large mixture of salts. For our second example, we have a black oil that contains a variety of mixed salts as well as formation water. So this is the composition on the left here. So you can see that this is very much a black oil, not as much methane, and a lot of heavier hydrocarbons. And Thermofast 2 does have the capability of trying modeling the heavy hydrocarbons fluid properties here. And so what we can see from this graph, so on the top, this is mixtures of 3 salts only, containing magnesium chloride, calcium chloride, and sodium chloride. And then on the bottom is the 40 formation water, the 6 salt mixture that I showed previously, as well as a case where it was lightly inhibited with methanol. So in terms of the average deviation overall, we can see that for the 40 formation water specifically, Thermofast 2, or the CASH model, does perform slightly worse than CPA Hydrates, but overall, you can see that the average deviation is about the same. What can we infer from this? So it may be possible that the CPA Hydrate model, Multiflash, is tuned specifically to this 40s formation water data set. And that's not necessarily a bad thing. It's good to be able to have your Hydrate model tuned to relevant data sets, but it does mean that you lose out a bit on the generality of the model. And we can see that for these 3 salt mixtures, that the CPA Hydrate model, the deviations are a bit higher compared to the CASH model. And so we can see that CASH model does perform on par overall because it's able to predict both of these system types generally. So now let's move on to our last layer of complexity. We've considered salts that have mixed salts in them. What happens if we include the effect of MEG, the thermodynamic hydrate inhibitor? And so what we can see, so we're looking at first at systems that have relatively low concentrations of electrolytes in total. You see that the deviations overall have a much wider spread compared to what we've seen previously. And then there's also really not much experimental data at these high concentrations of MEG. So here, for 2 to the 5 weight percent, in terms of experimental data, there's nothing beyond 40 weight percent. And similarly, here there's nothing beyond 50 weight percent, where you might be having to inject more MEG in practice. And so, despite the fact that the salt-MEG interaction is not really well described in any electrolyte model in literature at the moment, see that the Cassidy model does perform on par with CPA hydrates in many of these cases, which is a promising result. If we then increase the electrolyte concentration even further, we can see that the limitations of the lack of data becomes even more apparent, particularly for the higher concentration systems here. And you can see that there's quite a wide spread of deviations here, showing that how modeling capabilities for these systems aren't really well developed yet. But we can still use these results as valuable because of the fact that we know that the model tends to overpredict the equilibrium temperature, and that means it's going to be shifted more to the right in reality. I'll talk more about this on the next slide. But what's promising with the CASH model in this case is that for the higher weight percent electrolytes, the NEO model does have a tighter spread and lower average deviation compared to CPA hydrates. So here we have a natural gas example with MEG salts, and what I want to highlight here is how the behavior of the models change as the aqueous system changes. So firstly, you have the composition with distilled water only. At this point, the models are going to be underpredicting the equilibrium temperature. So in reality, the hydrate curve is going to be more to the left than, more to the right than it is predicted. When you add salt to the mixture, then the hydrate deviation shifted here. So now the model is overestimating the equilibrium temperature, which means you're predicting here, but in reality, it's going to be further in to the left. So it's going to be a lower temperature, which means you have more room more buffer room in terms of how you apply your MEG strategy. And you can see that as you begin to add MEG to the existing salt, that the deviations are going to shift lower and lower. So this highlights why it's important to understand the behavior of these systems that contain both MEG and salt, because the synergistic inhibition will work to provide more inhibition than the sum of its parts. But of course, this is not necessarily going to be a trend that's seen in all natural gases. It's something that's going to be system specific, which is why ultimately it's important to, when you try and understand what's happening here, is you get your natural gas reservoir fluids experimentally measured in the lab, where you can get measurements for these complex aqueous systems. This helps develop models, and it also gives you confidence in using those models to predict the equilibrium temperature for your system. And we have capabilities at Equilibria of doing this. So that is my talk. So I've demonstrated a new electrolyte model extension for the KH-phase hydrate model, which is purely predictive for hydrate equilibrium. And we've shown that this model is accurate over a wide range of systems, and it's on par with multi-flash in many of these cases. And so the way forward from here is having an automatically retunable model. And why is this something that we want to have? So I've talked a bit about tuning, but it enables flexibility and improves prediction accuracy. So the way we currently tune models, we try and make them as general as possible to capture as many different system types as possible. But if we could tune models on the fly to systems of interest, then we can make those models as accurate as possible for the systems, but also maintaining the flexibility of having a general model that can predict as many systems as possible. So if you're looking at a reservoir fluid of your own interest that has a specific composition, maybe it has a lot of carbon dioxide, maybe it has some hydrogen sulfide, then you can ideally update your hydrate model parameters to fit that set equilibrium curve as best as possible. So that's something that's actually quite beneficial to have if it's something that you can do quite easily. Also ensures that the model performance is up to date with trending experimental data, whether that be from the literature or whether from any measurements that you make of your own fluids. And so allowing for you to input experimental data is the way to go with that. And it also means that you can assess whether you need to reteam the Hydrate model. So if you put your own experimental data in, compare it to the Kasky model and see what the Kasky model predicts. If it's spot on, then nothing needs to be changed. But if there's something that's quite different, then maybe the Kasky model parameters need to be updated. That's all from my presentation. I'm happy to take questions now. Thank you.